All right, we're gonna finish the chapter 3 or exam 3 study guide. Yes. There's only one online lab. Oh, yeah, correct. Yeah, they won't be counted as late if they're not turned in Thursday. Oh, the following Thursday. Yeah. Okay. 9. All right, so we are on number 10. All right, so two R values are given on number 10 with different units. One that has units of joules, one that has units of calories. And so if you take and divide those two values, so R divided by R, which is 1, all right, if we take the 8.314 joules per mole Kelvin and divide by the 1.987 calories per mole Kelvin, we see that the moles Kelvin are going to cancel. And so when you take your calculator and you take your 8.314 and divide the 1.987, you get the actual conversion of joules to calories. So there are 4.184 joules per calorie. All right, and so when we had our conversion, I said that there's 4.184 joules is equal to 1 calorie. Right? And that's how you can get it. If you have R values given to you, you can come up with your own conversion. Because R divided by R, that's the same thing, it's just different units. All right, so we're going to need that conversion of 4.184 joules is equal to 1 calorie to solve the problem here, which has a bullet in a gun that has a mass of 235 grains, which is a unit of mass. All right, and so no one knows what a grain is. Well, someone does, I'm sure, but I don't know anyone that knows that a grain is 8.0648 grams. All right, so that is what a grain is. 1 grain is equal to 0.0648 grams. All right, so we can easily convert that into grams. All right, when you shoot the bullet out of the gun, there is a speed of 2.52 times 10 to the third feet per second. All right, and it is to now calculate the kinetic energy in joules and calories. All right, so kinetic energy, the equation is 1/2 mv squared. So you need to know that your mass has to be in kilograms. Your velocity has to be in meters per second. Because when you get a kilogram meter squared per second squared, that is a joule. You need to know the units that make up the joule. You need to know that that is a kilogram meter squared per second squared. All right, so what that means is we got to convert our mass into kilograms, and we have to convert our velocity into meters per second, and then we can plug it into the equation and get our answer in joules. All right, so you take your 235 grains, and you have 1 grain is 0.0648 grams, but we want that in kilograms. All right, so kilograms, kilo is 10 to the third, so 1 times 10 to the third. So your grams will cancel, your grains will cancel, and you now have the mass of the bullet in kilograms. So 235 times 0.0648 divided by 1 times 10 to the third. And it is a 0.0152 kilograms. All right, so now we have the mass in the correct units. Now we have to convert our 2.52 times 10 to the third feet per second into meters per second. All right, so we have to get rid of feet, and what do we know about feet? Well, it's 12 inches. All right, so the feet cancel, and now we are in inches per second. What do we know about inches? Well, we know that there are 2.54 centimeters in 1 inch. Inches cancel. All right, but we don't want centimeters, we want meters, and we know C is 1 times 10 to the minus 2. So now we will have our units in meters per second rather than feet per second. So you take your 2.52 times 10 to the third times 12 times 2.54 times 1 times 10 to the minus 2, and you get 768 to 3 sig figs meters per second. All right, so now you just plug those things into the equation. You now have the right units. And so your kinetic energy is 1/2 of the mass, 0.0152 kilograms, times the 768 meters per second squared. All right, so square that, and then multiply that by the 0.0152, and then divide that by 2. And my kinetic energy to 3 sig figs is 4.48 times 10 to the third joules. All right, so we have now the kinetic energy in joules. Now we convert it to calories, and we have our 4.48 times 10 to the third joules. All right, so we have to then have joules, we have to have calories. We go up above where we took the R divided by the R, and we see that the 4.184 goes with the joules. So the 4.184 goes with the joules per calorie. And so we have to then divide this by 4.184, and we get 1.07 times 10 to the third calories. All right. So either the R values are going to be given to you, and you can take the R divided by the R to find the conversion factor, or the conversion factor of 4.184 joules per calorie will be given. It is not something you have to memorize, but it may be something that you have to get by taking R divided by R. All right. That was number 10. Number 11. Number 11 has a reaction to NH3 gas plus 3O2 gas plus 2 CH4 gas yields 2 HCN gas plus 6 H2O gas. All right, so this reaction, all of the reactants and the products are gases. So you can read it in terms of moles, always any reaction in moles. 2 moles reacts with 3 moles and 2 moles to give 2 moles and 6 moles. When they're all gases, then and only then can you use volumes. You could say 2 liters of NH3 reacts with 3 liters of oxygen gas and 2 liters of CH4 gas to produce 2 liters of HCN and 6 liters of H2O. You can only use a volume when everything is a gas. All right, so question A in number 11, calculate the delta H for this reaction. All right, so when you're given a reaction, you got to find delta H. You go to your table, you find your delta H naught formations. For your NH3 off of table 6.2, I believe, it's going to be given to you on the test. And that is a negative 45.90 kilojoules per mole, right off of the chart. Oxygen is an element in its natural state. It is 0 kilojoules per mole. All elements in their natural state have a delta H naught formation of 0. The CH4, negative 74.87 kilojoules per mole. The HCN, 135.1 kilojoules per mole. And finally, the H2O gas, be careful, there's H2O liquid, there's H2O gas. So the gas, negative 241.8 kilojoules per mole. All right, so to find the delta H naught of reaction, you're going to take and add up the delta H naught formations for all of the products. And then you're going to subtract all the delta H naught formations of all of the reactants. So it is the products minus the reactants. All right, so the products, we have 2 HCN, and each HCN is 135.1 kilojoules per mole. And so we're going to take 2 times the 135.1 kilojoules per mole, because that's 2 moles in the balanced chemical reaction. All right. And also a product, we have 6 waters. Each water, negative 241.8. All right, so we have 6 moles of water, and we have negative 241.8 kilojoules per mole. And so the moles here, 6 moles, cancel here. All right, and that is your products. So when we find our delta H naught for this reaction, we take our products, and then we subtract our reactants. Our reactants are NH3, negative 45.9 kilojoules per mole, 2 moles. So 2 times the negative 45.90 kilojoules per mole. And that's 2 moles. They cancel. All right. We have 3 times 0. It doesn't matter what times 0. It's always 0. Anything you multiply by 0 is 0. I do not put that in. You can put 3 times 0 if you want. That is 0. All right, so here we have 2 times negative 74.87. So we have 2 moles times the negative 74.87 kilojoules per mole. The moles cancel. All right, and so that is our reactants. So we have the products minus reactants. I highly recommend getting a number for each one of those before doing the whole thing on your calculator. All right, so I have on my calculator, I'm going to write 135.1 times 2 plus 6 times my negative 241.8. And then I'm going to push equals, and it is going to give me that the products is negative 1,180.6 kilojoules. All right, so that is my number for my products. Then I'm going to do my reactants. I'm going to take 2 times negative 45.90 plus 2 times negative 74.87. And that is going to give me a negative 241.54. All right, and so then I'm going to take my negative 1,180.6, and then I'm going to subtract a negative 241.54, and that will give me negative 939.1. Negative 939.1 kilojoules. All right, so many times, almost every time when you calculate a delta H, it will ask if it's endo or exothermic. Anytime you get negative, that is an exothermic reaction. It may ask if you're holding on to the flask that this reaction is taking place. Does it feel hot or cold? Exothermic releases heat. This is hot. Okay. All right, so that is part A. It's simply the products minus the reactants. All right, so now we're going to do part B. In part B, it says calculate the heat when 25 grams of CH4 reacts. So calculate the heat when 25.0 grams of CH4 reacts. All right, so now we have to look at the reaction that we just did, and that is you get your negative, you release 939.1 kilojoules, and we're looking at the CH4 for 2 moles of CH4. All right, and so we have to convert our 25 grams of CH4 into moles. So 25.0 grams of CH4, 12 plus 4 is 16.05 grams per mole off the periodic table, carbon plus 4 hydrogens. So now we have moles of CH4. And so what we have is we release 939.1 kilojoules in the balanced chemical reaction for 2 moles of CH4. Again, we go back up to the balanced chemical reaction, and that is for 2 moles, right here, 2 moles of CH4. That is the amount of energy we get released for 2 moles of CH4. All right, so when we take our 25.0 divided by our 16.05, we see that we have 1.56 moles of CH4. And so then we multiply that by the negative 939.1 and divide that by 2. And we see that we are going to release negative 731 kilojoules. All right, so when 25 grams of CH4 reacts, 731 kilojoules of heat is released. It is exothermic. All right, part C. All right, so part C is Avogadro's law, where you have all of your reactants and products gases. We can use volume ratios. All right, so we're going to take 10 liters of each reactant. All right, and then it says what volume of HCN would be formed. All right, so we have our balanced chemical reaction, all right, where we have we're going to have 10 liters of each reactant. So we're going to have 10 liters of NH3. We're going to have 10 liters of oxygen gas. And we're going to have 10 liters of CH4. All right, and so now in our balanced chemical reaction, since again everything is all gases, we see that the coefficient of 2 in front of the NH3, so we have 2 liters of NH3 would produce 2 liters of HCN. All right, and so this would give us 10 liters of HCN. From our balanced chemical reaction, we have a coefficient of 3 in front of the O2, so 3 liters of O2 would produce 2 liters of HCN. Again, that's the balanced chemical reaction coefficients. So 6.67 liters of HCN can be produced from that amount of oxygen. And then you look at the coefficients for your CH4, that is 2 liters CH4 and 2 liters of HCN. So 2 liters of CH4 would produce 2 liters of HCN, and this would give us 10 liters of HCN. All right, so again, the one that gives you the least amount of product, that is your theoretical yield. All right, and that means that O2 would be the limiting reactant. And so the theoretical yield, the most volume that you can get for HCN is 6.67 liters. And so the next problem says if 6.0 liters of HCN was produced in this reaction, so this is part D, calculate percent yield. All right, so that's the actual divided by the theoretical and multiply by 100. So they have to give you the actual yield in lab, the volume that was actually produced, 6 liters. The theoretical yield that we calculated, 6.67 liters times 100, and that gives you a 90% yield. So that would be a 90% yield for this reaction. All right, again, you can only use volume ratios when you have all gases. All right, so let's do, I'm going to add something. I'm going to make it part E. All right, to this problem, I want to know, I have a reaction, HCN plus 3 H2O yields NH3 plus 3 halves O2 plus CH4. All right, so what you can't see because it's up there further is that the initial reaction was 2NH3 plus 3O2, all these are gases, plus 2CH4 yields 2HCN plus 6H2O, and we calculated that delta H to be a negative 939.1 kilojoule. I think that was our number, negative 939.1 kilojoule. All right, so the question here is, I then manipulated this reaction and I say calculate delta H. All right, so you have to see what has changed from the reaction here to the reaction here. So you should see that the reaction has been reversed. My reactants are now my products are now my reactants. So I reversed the reaction. So that means I have to change the sign of delta H. So instead of negative 939.1 kilojoules, I changed the sign when you reverse the reaction. So now it is a positive 939.1 kilojoule. Then you see that I had 2 HCNs and 6 H2Os. Now I only have 1 HCN and 3 H2Os. So you see that I divided this reaction through by 2. And so I have to divide my delta H by 2. And so this gives me a 4, 6, 9. Let me do that. So you got your 939.1. 939.1 divided by 2, 469.55. And so to 1 decimal, you would then put 6 and kilojoules. So the delta H for this is now endothermic. So anytime you have an exothermic reaction, you reverse the reaction, you now have an endothermic reaction. All right, and so when you divide all the coefficients through by 2, you have to divide the delta H by 2. All right. So here we have 1/2 N2 plus, we're still on problem number 11. This is, doesn't have a letter, we'll call it F. All right, 1/2 N2 plus 3/2 O2. Oh, H2, sorry. 3/2 of H2 yields NH3. The delta H for this is negative 45.9 kilojoules. When we take carbon, solid graphite, plus 2H2, I get CH4. Delta H for this is negative 74.9. When I have 1/2 H2 plus carbon plus 1/2 N2, I get HCN with a delta H value equal to 135.2 kilojoules. And when I have H2 plus 1/2 O2 yielding H2O, I have a delta H value of negative 241.7 kilojoules. All right, so this time we're going to use Hess's law, all right, to find the delta H. So we have, we're going to go with our 2 NH3 plus 3 O2s plus 2 CH4s yields 2 HCN plus 6 H2O. All right, so when you use Hess's law, this is a Hess's law problem. All right, so we already did this one by products minus reactants. So there's going to be some on the test where you have to do products minus reactants. There's going to be others on the test where you're going to have to use Hess's law. All right, so when you have, we have in this case 4 reactions. All right, and so we have NH3 down here, and there's only one reaction up here that has NH3, and that's the first one. Note that we need to have NH3 as a reactant, not a product. So we have to reverse that reaction to get NH3 as a reactant, because that's what the problem is giving us. All right. The problem also has a 2 in front of the NH3. So we have to reverse this reaction and multiply it by 2, which means we have to change the sign of the delta H and multiply it by 2. And so we have 2 NH3 yields N2 plus 3 H2 with a delta H that is now positive and multiplied by 2. So it is a positive 45.9 times 2, which is a positive 91.8 kilojoules. All right. Your oxygen. All right, 3 O2s here. Well, we're going to skip that one. We're going to go to the next reaction, which is your CH4. It's right here. All right, the only place you see CH4 is here. And so we need 2 of them. And again, we need 2 of them on the reactant side. So we're going to do the exact same thing again. We have to reverse it and multiply it by 2. Because CH4 has to be a reactant and there are 2 moles. So we're going to reverse it and multiply it by 2. So we have 2 CH4s We multiply it by 2 carbons, and 4 hydrogens. And the delta H for that reaction is we have to change the sign, so now it's positive, and we have to multiply it by 2. And that is a 149.8 kilojoules. All right, so the next one we come to is HCN, and we need 2 HCNs. We look up here, HCN, it is on the right side, so we're going to keep it as a positive delta H. However, we need 2 of them, so we have to multiply this through by 2, and then multiply the delta H by 2. All right, so we're going to multiply that by 2, and so we're going to have H2 plus 2 carbon plus N2 yields 2 HCN. And the delta H of that is we have to multiply this by 2. So it is equal to 270.4 kilojoules. All right, so then finally we see our water. We have 6 waters. And we also have 3 oxygens. And so this works out nice because we need to have 6 waters. It has to stay on this side. And so we have to multiply it by 6. And so we have 6 H2s plus 3 O2s, which is what we needed as well, yields 6 H2O. And then the delta H of that is you take your negative 241.7 and multiply that by 6, and you get a negative 1450.2 kilojoules. All right, so now we have all of them taken care of. Now we're just going to add these 4 reactions up. All right, so when we add these 4 reactions up, we also are going to add up the delta H's. But first, you have to subtract on both sides what is the same. All right, and so on this side, we have 7 hydrogens. 6 here, 1 there, 7 hydrogens. Over here, we have 7 hydrogens, 3 there, 4 there. So we're going to subtract 7 hydrogens from both sides. The hydrogens are gone. Carbons, we have 2 carbons on the left. We also have 2 carbons on the right. We subtract 2 carbons from both sides. They are gone. Nitrogen, we have 1 N2 on the left. We have 1 N2 on the right. We subtract them. They are gone. And now we have subtracted everything that can be subtracted. So now we bring down all of our reactants. 2NH3 plus 3O2 plus 2CH4 yields 2 HCN plus 6 H2O, which is the reaction that was asked for. Add them up, you get that reaction. So now we add up all of our delta H values. All right, so we take our negative 1450.2 and we add 270.4. And we add 149.8, and we add 91.8, and we get negative 938.2 kilojoules. So apparently I was off by 1. Not sure how I got a 9 and not an 8, but so the answer should have been identical. So I plugged in a number wrong in one of these. Which number did I plug in wrong? I don't know. But one of these numbers was plugged in. They should have been identical. All right, so anyway, I inputted a number slightly different. Probably that 87 is my guess. So anyway, the numbers should have been identical. I'm pretty sure this one was right. Negative 938.2. That would make sense. All right, so again, it's exothermic. It should be exactly the same as the one above. I just probably didn't put the 8.7 in when I put in the numbers. All right, so this is Hess's law. So you have to know how to do your Hess's law as well as products minus reactants. Number 12. Number 12. Calculate the volume of 6 moles of gas at STP. All right, so there's probably a lot of questions about STP. So calculate the volume of 6 moles of a gas at STP. When I have STP, I will write a 01 after it so I don't forget that my temperature is 0 degrees Celsius and my pressure is 1 atmosphere. I never forget the 1 atmosphere, all right? But sometimes when you say standard temperature, many times that's 25. STP is a gas standard temperature, and that is 0. Of course, we don't want that in Celsius, so that's 273.15 Kelvin. And that's a perfect, well, that's 5 sig figs and a perfect 1 atmosphere. All right. So STP, there is a constant that goes with STP. Anytime you have STP, you have 22.4 liters per mole. All right. And so we can derive that number. And if you're taking a standardized test, I highly recommend knowing that number because there's a lot of questions with STP. That 22.4 will get you the answer quick. All right, because like this one, what's the volume of 6 moles? You simply multiply it by 6, and you have your answer, which is a 134 to the correct sig figs, 134 liters. All right, so the other way to do it is, of course, PV is equal to nRT. And we want to know the volume. So the volume is equal to nRT over P. All right, so they say 6 moles. So you put in your 6 moles. The R value for PV is equal to nRT is always 0.08206. And you have to know your temperature at STP is 273.15. And then you divide that by the 1 atmosphere. All right, and so that again will give you 134 liters. All right, so the 22.4 is simply, all right, so since STP, that's always a 1. All right, so you have the volume, and if we divide this, volume is, well, divide both by N. All right, so what we have is we have RT over P. And so the 0.08206 liter atmosphere per mole Kelvin. The temperature is 273.15 Kelvin. And then the pressure is always 1. So then you divide it by 1. All right, and so the volume per mole at any gas at STP is 22.414 if you wanted more sig figs. And that is liters per mole. Most of the time we will go with 3 sig figs. If you want 3 sig figs, 22.4. If you want 4 sig figs, 22.41. All right. If you want to carry it out and not have that determine the number of sig figs, 22.414. Again, you just take your 0.08206 and multiply by 273.15, and you get your, it's a 5. Okay. 22.41. Actually, it's a 5. But it is a 4, 6, 8, 9. All right, so usually you'll go with 3 sig figs, 22.4. That will get you the answer to any multiple choice problem. All right, so whether you use the 22.4 multiplied by 6 or put it in PV is equal to nRT, it doesn't matter. It gives you the same answer, 134 liters. All right, number 13. So for number 13, it says to write the reaction for delta H naught formation of HCN. All right, you have to know the definition of delta H naught formation. That means you're going to be formation. So F is the formation, and it's very clear that it's formation of 1 mole, not more, 1 mole from elements in their natural state. Or standard state. All right. And so when you have HCN, which is our problem here, so we're going to form 1 mole of HCN from elements in their natural or standard state. Hydrogen is diatomic. You have to know that. So the standard state of hydrogen, H2. The standard state, the natural state of carbon is not diamond, it is graphite. Carbon, solid, graphite. The standard state of nitrogen is a diatomic gas, N2 gas. All right, and we have to leave this as a 1. So many times when you're writing this reaction, you're going to have to use fractions. All right, so that is a 1/2 to give you 1 hydrogen and a 1/2 to give you 1 nitrogen. All right, and so this can be a very simple question if you know the definition, or impossible if you don't. All right, so you got to form 1 mole. It has to be 1 mole, not more than 1 mole, from elements in their natural state. Hydrogen, carbon, and nitrogen are the elements in HCN. And that is your delta H naught formation. All right, so above here are 4 reactions that I gave you. All 4 of these are delta H naught formations. All of these are delta H naught formations. All 4 of these delta H naught formations. And you see that this is exactly what I wrote, except I wrote gases and I wrote solid graphite. All right, but that is the exact reaction that I wrote. Again, all of these are forming 1 mole. So all of these are forming 1 mole. So I got 1 mole of my NH3, 1 mole of my CH4, 1 mole of my HCN, 1 mole of my H2O, and they are all from elements. The first one, nitrogen and hydrogen. Second one, carbon and hydrogen. The third one, hydrogen, carbon, nitrogen. The fourth one, hydrogen, oxygen. All right, so they are all elements in their standard state, forming 1 mole of product. All right. We will keep reviewing tomorrow. Again, if you have questions, bring those in and we will go through those.